Hi to Leo students, Mr. Kaczynski with you. Going to do 5.1 practice your skills here, solving systems of equations graphically. Here we go, and checking algebraically. Verify whether the given ordered pair is a solution to the system. If it's not, explain why. All right, so let's start off with this top equation, and what we're going to do is, we're going to see if this is true. If 0.2 equals 47 plus 3 times x, which is negative 15.6. So let's type that into our equation here. 47 plus 3 times negative 15.6. And that gives us 0.2. Okay. Well, that's only half the battle. It works in this top equation, but we also needed to get it to work in the bottom equation. So let's go again. Let's go 0.2. Does that equal 8 plus 0.5 times negative 15.6? All right, so I'll just do 8 plus 0.5 times negative 15.6, and that gives us 0.2. So we'll just say yes, I guess. Yes, this is a solution. Because it works in both equations. It is a solution to both equations. That makes it a solution to the system. Let's do it again. How about we, take some shortcuts here. 15 minus 2 times x, which is negative 4. And we want this to be equal to 23. It is, okay? And then we'll do 12 plus x, which is negative 4. And that's not 23. So this is a no. And I think I'll type this in for speed here. The point doesn't satisfy. How about, yeah, satisfy the second equation. All right, we go over to this one. Let's go to the y equals button. Try it a different way here. We'll go 4.5 plus 5x. And then we'll do the second equation, 2.3 plus 5x. Well, how could this possibly be true? These both have the same slope with a different y-intercept. They're never going to cross each other on a graph. So there's no solution to these two equations, actually. We can see that in the table here, too. If we go to 2, one's got an output of 12.3, but the other one doesn't. So I'm going to say no. And you can explain this a couple of different ways. It works in the second equation, but not in the first. Or I'm just going to say these are parallel lines, so they won't have, so how about so the system won't have a solution. All right, let's try the same way down here. Let's punch in this equation, 12x minus 35 and 5 minus 8x. Let's go to the table, and we're going to go to 2, and we do get negative 11 for both of these, so this is a yes, because 2 gives us the output of negative 11 both times. All right, I think I'll keep on with this method here. Let's go 8 plus 2, parentheses, x minus 11. And then I'll do 1 minus 3 x. And then I'll go to the graph this time. And let's see if they both cross at 3, negative 8. Oh, looks like it's close here. Let's go trace 3, enter. And that gives me negative 8. And if I press up, I'm on the second line, and I go 3, enter. That gives me negative 8 as well. So this is yes. And the last one, maybe we'll use some mental math here. How about 4 minus 8 is negative 4. Negative 4 times 3 is negative 12. And negative 12 plus 12 is 0. Works in the first equation. And then 4 plus 4 is 8. 8 times negative 3 is negative 24. And negative 24 plus 24 is 0 as well. So yes, each time we put 4 in, we get 0 out. If I had more time, I'd probably verify that with the calculator, but I think we'll move on now. Graph each system on your calculator using the window given. Use the trace function to find the point of intersection, and does the calculator give you approximate or exact solutions? All right, so we're going to go to y equals. We're going to put in both of these equations. We're going to go to the window, and we're going to set it up for a minimum of negative 18.8 with 18.8 as the maximum and 5 as the scale. And then for the y minimum, negative 12.4, y maximum 12.4, and scaled by 5s. Oops. Oops, I didn't enter my equations right. There we go. All right, let's graph these. Oh, did something wrong here as well. Oh yeah, I want negative 9, not a minus sign. There we go. And it looks like they're going to cross at somewhere just shy of 2 and just above 1. So I'm supposed to use the trace function. I'm going to say it's about 8.4 and 7.2, or maybe 8 and 7. So let's see, 8, 7 is on one of the lines. 8, 7 is on the second line. So actually the solution is 8, 7. And in this case, I was able to find the approximate solution, but I did have to kind of guess and check a little bit there. All right, let's do the second one. First equation, 4x minus 5.5. Second equation, negative 3x plus 5. We're going to change our window here to negative 4.7, positive 4.7, scaling by 1s, and negative 3.1, positive 3.1, scaling that by 1s. We'll hit the graph. Looking for where these two lines cross. Looks like they cross at about 1.5. Yeah, maybe 1.5.5. That's definitely on the first line. Let's go to the second line and put in 1.5. Yep. So just looking at the graph doesn't give us the perfect solutions. We have to kind of take educated guesses and check them in both to make sure that's the case. We can also go to the table and we can, well, actually we can't see the 1.5, 0.5. I'd have to change my table set to go by 0.5s. Then I could look at the table and see that at 1.5 I get the same outputs both times. All right, estimate the coordinates of the point of intersection for each pair of lines. K and L. So K right there, L right there. Looks like they intersect right here at 2, 5. No big deal there. How about M and N? M and N right about there. Ooh, so I'm going to guess about negative 2.8, 4.2. I know it's not negative 3 exactly, and I know it's a little bit more than 4, so negative 2.8, 4.2, something around there. Maybe if you said negative 2.9, 4.1, I'd understand why you said that as well. K and M. K and M right about there. It looks like about 1.5 and 6. Just estimating. And L and M. So L and M right about there. It looks like it's just past the 3. So I'm going to say 3.1. and almost to the 7. I'll say 6.7, something like that. Be interested to see how many people have the exact same solutions as me. Match each graph of a system of equations to its corresponding table values. The tick marks are each 1 unit apart. Okay. So on this first I choice here, all the outputs are 4, and 1, 2, 3, 4. That's right here. The other one has a slope of 1. I can see the y value is going up by 1. So C has got to be table I. Okay. What about 2 here? We got one that's going down, another one that's going down. Y value is going down, Y value is going down. Do we have any 2 negative slopes? Yep, D has got 2 negative slopes. All right. Same idea here. On 3, Y1's got a positive slope because the values are going up. Where so does Y2. Those are both going up. So this has got to be 3. Also, you can see they both intersect at 6, 5. 1, 2, 3, 4, 5, 6, and 5. That might be more so the point 6, 5 right there. And if we go back to 1 here, 4 and 4. That's the output. 4, 1, 2, 3, 4, right there. And then on this one we had 3 and 3. So 3 and 3 is right there at that point. And obviously that leaves 4 for this one. We can see 3.5, 6.5, 1, 2, 3, 3.5, and that's 6.5 up right there. You can also see the values of Y1 are going down, the values of Y2 are going up. So, all right, write a system of equations for this one. Okay. So let's do this line here. We'll call it L1 here. And we're going to do, the y-intercept is 2. Looks like the slope goes up 3 over 2. So we'll go y equals 3/2 x. Oops. 3/2 x plus 2. And then we'll call this one L2, line 2. And it's got a slope. Well, how about we use this point, which is the point 2, 1. And let's see, what's another point that it goes through? Approximate, well, maybe that one. So it's got a slope of -2 over 3. So we'll write this in point slope and we'll say -2/3 times x minus 2 plus 1. So that would be our system of equations right there. All right, that's it for 5.1. Practice your skills. Hopefully that helps you and you've caught your mistakes. Good luck, and I'll see you soon.